Bu şekilde de
Bana da izin verebilir misiniz? Ben de
sana da vereyim. Hemen sana da vereyim. Dur. Ve diyoruz ki ama sana izin verince al sana recording in progress. Bakalım. We are going to talk about further calculations on assets and base. Further calculations means calculations involve weak assets and weak bases. But very firstly, I believe we need to define what is weak asset or base. Do you have any idea, baby? What means weak in chemically?
The less H ions it's produced.
No, baby. Okay. Generally, at the same concentrations, weak acids produce more pH, which means they are producing less hydrogen plus ions. For the base, the same stuff. Weak bases at the same concentration with the strong ones, they produce less pH, but it's not defined by pH, baby. pH means those guys, both acids and bases, are not 100% ionizable. Means, for example, HF is one of the most popular weak acids of them all. In aqueous form of HF, we have an equilibrium between ions and chemical original itself. They hold in aqueous state. Means what? If we have, let's say, we have 10 to 1 molar of HF. Normally, if HF was one of stronger acids, it produced 1 molar of hydrogen plus and 10 to 1 minus 1 molar of F minus. But since HF is not a kind of strong acid, it produced less those type of ions. For example, let's say it's something icy, not E, the C, nice. We may say that only, let's say, 1% of it may ionizable, baby. And this will yield what? If 1 molar of HF produce 1 molar of hydrogen plus, 10 to 1 molar of it will produce half. Then the result will be 10 to minus 3. That means 10 to minus 3 much of HF will ionize to produce that concentration of ions accordingly. Then we have what? We have the concentration of minus 1 minus 10 to minus 3 and the origin, the new freshly produced ions. For AP calculations, baby, generally we may omit that value because up to 5% can be omittable for such kind of calculations because it has no meaning, baby. To subtracting such kind of things, it's no meaning subtracting 1 from 100. It will be meaningful after 5. Let's say 6. Okay, it's meaningful because the result will be something 94. But for this time, you will end up with something 99, and 99 is almost 100. To make our life easy, just like physics, we assume that, okay, almost no concentration for starting acid is consumed. Then we have such kind of equilibrium state, which contains concentration of 10 to minus 3 and concentration 10 to minus 3 and concentration 10 to minus 1 accordingly. Those are concentrations for products and the reactants. Then the ratio will be something 10 to minus 5, which can be stated as dissociation constant for a weak acid. Okay, this is just the same thing as equilibrium, baby, because we still have equilibrium between starting materials, reactants, and products. But in that kind of reactions, our starting material is a kind of acid, and products are the ions of that acid. The phenomena is those weak acids or bases are not 100% ionizable. Okay, this is the case. Let's say if we have two acids, one of them HA, the other one is HB, and one of them has the K value is something 10 to minus 5, the other one Ka value is something, let's say 10 to minus 7. Which one is stronger, baby?
10 to minus 5.
Yes, because it's a bigger number, a bigger division. It's, we may say that for, let's say, both have 10 to minus 1 molar of starting acid concentrations. The upper one, just like our previous example, has HA and A minus. Then we have 10 to minus 1 molar of acid concentration at the beginning. Since we will omit the consumed up concentration for HA, it has no meaning to use ice table for such kind of calculations. We just say that, okay, just forget about ice. Simply put X's for ions of weak acid. Okay? We just jump to the equilibrium part immediately. Then we will say that this Ka value will be something ratio between product and reactant, and it also has numbers as x's and some 10 to minus 1s, which should be equal to 10 to minus 5. Then x square will be 10 to minus 6, and x will be 10 to minus 3. Okay, baby? Then let's put this concentration here. Okay, then check for the value for HPN. Also, let's say the pH value of this guy is something 3. And normally, what it should be? Normally, it should be pH 1. If HA were a strong acid, the pH value will be 1. Okay, let's make calculations for the B guy. The HB have the same story. It will ionize partially with the starting concentration 10 to minus 1. And let's put Y's for concentrations of ions. Then 10 to minus 7 will be equal to Y times Y high 1, Y we set. Then the Y will be 10 to minus 4 molar, okay? And pH will be what? The pH will be 4. As I told you previously, the weak acids have more neutral pHs than the normal. And even for two weak acid case, the weaker one should be even closer to the pH more than the slightly stronger one. Okay?
Okay.
You may easily say that. For example, let we say we have 10 to minus 5 molar of, let's say, HC, and we have 10 to minus 1 molar of HD. And the previous one has the pH of 5, and the lower one will have the pH of 2. And I just want to ask you, which one is weaker, baby?
pH 5 is weaker.
No, baby. This is just the case. Let's make calculation. Since HD has a concentration of 10 to minus 1 molar, if everything was en route, the pH should be something 1. But we observe that the pH is something 2, which means not 8. This is D. HD is partially ionized acid. We said, we observed that 10 to minus 1 and also 10 to minus 2 and 10 to minus 2. In that case, the ionization is something, as you see, 10% of ionization, and this calculation is not valid, baby. But I just want to show you. And we will say that, okay, this guy has a key Ka value, which is something 10 to minus 2 times 10 to minus 2, 10 to minus 1, and 10 to minus 3. Okay, it's not so weak, but it's a weak base, weak acid. But for the case of upper one, baby, this acid originally low in concentration, baby. And, and normally it should have pH of 5, and it does. That means this is strong one.
Okay.
The pH value of HC is really close to neutral pH, but it is just because of its low concentration at the beginning. HC ionized 100% paper. Due to the fact that can't say a correct answer just looking at the pH values of acids and bases. You have to check whether if everything is all right. For the case of HC, okay, this is a normal case because normally it has the concentration of 10 to minus 5 and pH should be 5 accordingly. But for the case of HD, it has a concentration of 10 to minus 1 and normally pH should be 1, what we observe pH 2, which is something more neutral. Then we may say that, okay, HD is a kind of weak acid.
Okay.
Okay, baby, I believe you get the idea.
Yeah, I got it.
The idea is just simply you have to state that, okay, if you have to check whether everything is on way or not. Okay, then. Let's see, baby, what we have. Then let's have, okay, then. Let's say we have HA. The concentration of HA is something 10 to minus 2 molar. And I said that ionization percentage for this one is something 0.1. This is what? This is actually, we may write it something like that. Do you have any idea what I'm writing, baby? What this one means?
Half.
This is 100%. This is 1000%, baby.
Okay.
While we are put double O's, then it means this is 1000%. That means 1 out of 1000, baby. Okay? Then I want to ask you two things. What is the pH value for this HA, and also what is the Ka value of this acid if we given this one is 0.1% ionizable?
First, we can do ionize it as XX.
Yeah, maybe we just want to do that. If 100 molar of HA will produce 0.1 molar of hydrogen plus, what will be the result for 10 to minus 2 molar? Just cross multiplication, okay? Then the x will be 10 to minus 2 and 10 to minus 1 divided by 100. Then this will be something 10 to minus 5. And h will be, let me write down it, pH will be something 5. Okay, baby?
Okay.
Okay, this is the case. Then now we have enough data to calculate Ka value, because very firstly, okay, you are doing right. We may put X's for ions while we are putting 10 to minus 2 for the initial concentration of HA. But we have no other information there.
First, we have to find those.
That's why we have to make this cross multiplication to find out what the x's are actually are. Then they are 10 to minus 5 and 10 to minus 5. Then, okay, it's easy. The Ka value will be 10 to minus 5 times 10 to minus 5 should be divided to 10 to minus 2, and which will yield so
10
many.
to minus 8.
Okay, this is the case. This is the case. This is quite normal. This is the normal calculation for a weak acid. Okay, this is the quite. There's two ways generally, maybe three. They will give you the concentration of HA and let's say pH. The pH will yield you concentration of HA, which is equal to A minus. Then by calculation from those concentrations, you may able to find Ka values, or they will give you Ka or HA, then ask you what the pH is. This is the second way. And for the third way, I believe you get the point. They give you Ka value and pH and want to ask what is the initial concentration of acid. Okay, let's do this one. Let's make a calculation and even further calculation for third way. Third way means what? I just want to say you that this one will be the not short answer, the long answer questions, one of the long answer questions. Let's say they said that we have HA which have the Ka value of 10 to minus 6. And we have 3 liters of it with the pH of 2. And they also state that, let's give additional information to make our question a little bit longer. The HA has a molecular weight of, let's say, 100 grams per mole. And they asking us how many grams of HA, X gram, should be added while preparing 3 liters of this solution, maybe. Okay. Very firstly, let's check what we have. We have a weak acid. Weak acid means we have an equilibrium. Then we have the Ka value, which means we have the ratios of those concentrations A as 10 to minus 6. Then we have pH. The pH value of 2 is hydrogen ion concentration is 10 to minus 2. We have this one. And it's obvious that A minus ion concentration should be the same. Then we can ask the Ka value what the initial concentration of HA is. Then let's check. 10 to minus 2 times 10 to minus 2 divided by X will yield this lovely guy. Then the X will be something 10 to minus 2. We have so many 10 to minus 2s, baby. No, sorry.
No,
this
10
is,
to minus 2 plus 2.
it is 100, baby. No? It's 100, baby. Yeah. What happened? Really?
Minus makes plus. So.
Yeah, it will be something. But this is really, this is quite ugly, baby. It's quite ugly. And let's say we have the pH of 3 instead of 2. Let's make it 3 because in that way, this solution is not preparable, baby. Let's make it those numbers as 3, those numbers as 3. And okay, finally, we have 1 molar of initial acid concentration. The HA concentration will be 1 molar. Then we will do what? We will do
The molar calculation.
to just find what the mole is. Then the volume is 3, the concentration is 1, the mole will be 3 moles. And we know that from the upper, we know that the 1 mole of it something 100 grams. Then we said that we should have to add 300 grams of weak acid while preparing 3 liters of initial solution. If we do so, then we will end up with pH 3 concentration solution base. Okay? Okay, baby, did you get the idea?
I got.
Okay. Then one more thing, I just want to warn you. For example, let's say, what may affect the Ka value? Affected by. What may affect the Ka value, baby? This is just the question. This is just the question of equilibrium, actually. You said pressure, no? No. The Ka value is just affected by temperature, baby. Do you remember? It just any equilibrium constants just affected by temperature. You said the pressure or concentration or blah blah things will affect the direction of equilibrium. But the Ka itself just affected by only temperature. And normally ionization of weak acid are something endothermic. And if we increase the temperature of examination, the reaction will go forward. Then, as going forward, the concentration of products will increase and the reactants are decreased. Then our Ka value will be increased, okay? But they will ask you some, okay, let me do some ugly things, okay? Maybe you guess what I'm going to do, huh, oh, baby? Something temperature? No, something related with my nose, because you know I'm quite illish, not ill, but something like that. Okay, baby, I'm now available for teaching. Okay, then. Let's say that they will ask you how the ionization percentage will affect it by adding some amount of water to the solution. What you say?
I think it would be true.
Let's say that if we add water to the whole site, the concentration of whole solutions should be decreased, no? Then, since we have 2 for this one, then what happened? The concentration, due to the concentration decrease, the equilibrium will shift it to the product side, okay?
Okay.
Okay, then we may say that while we are producing such kind of thing, the ions, such ion production of ions, then we will observe that the ionization percentage of ions should be increases. Any effect which altered the direction of equilibrium as forward, the ionization percent should be increases, babe, okay? For example, initially we have such kind of 1% ionization. Then, while the equilibrium shifts to the forward side, let's say 2 more ions are produced. Then we have what? We have 3 concentration for ions, but 97 concentration for the initial acid concentration. Then we have what? We finally state that, okay, while the equilibrium shifts to the product side, the ionization percentage is increased. Okay, baby. Initially, it was 1% ionized, then now it became 3% ionized, baby. Okay? This is the case. This is the case. As we said that, as the concentration of ions increased, the ionization percentage should be increased accordingly. Then I just want to ask, what happens if we add some more concentrated hydrogen plus to the system? How the ionization percentage affected by addition of a stronger acid, baby? Let's check. We have H plus and A minus. Then we are adding what? We are adding what, baby?
Hydrogen plus.
Hydrogen plus, and the reaction should be shifted to the what? Forward or backward?
Backward.
Then reaction shifts to the left, and which resulted in increase or decrease on ionization percentage?
Increase.
Not increase, baby. Let's check. Let's say we have 10 and 90 ionized acid, weak acid we have. And we have initially what? We have initially 10% ionization. After shifting to the product reactant side, we will state what? Let's say 92 and 8 and 8. What happened? The ionization ratio, ionization percentage decreases to 8%.
Okay.
Okay, then we may say that any effect which changes to the direction of weak acid ionization to the product side, forward side, will increase the ionization percentage. And just the opposite, any effect which shifts the reaction to the left, to the product side, it will decrease the ionization percentage. No? Because while shifting to the back, you are producing less product, baby. And your products are ions. And since you are producing less ion, meaningfully your percentage ionization is decreases. Okay? Just for the other way, anything which increase the concentration of ions, since you are producing more ions in the solution, will shift it as increase in ionization percentage. Okay? Okay, this is the case, baby. Did you get the idea?
Yeah.
Then, quite finally, I want to tell you what about the neutralization of weak acids and weak base. For example, let's say we have 1 liter and 0.1 molar of HCl, which is what? Which is simply by multiplying those two, 0.1 mole of HCl, no? And this one requires 0.1 mole of, let's say, sodium hydroxide to neutralize, as we talked previous lectures. Okay? For the case of, let's say, for the case of HF, which has a Ka value of 10 to minus 5, then 1 liter and 0.1 molar, but we have what? The pH of 3. How many moles of sodium hydroxide is required to neutralize this HF solution vapor? Normally, you have to do this one. since multiplication of volume and molarity will yield you mole, then you have 1 times 10 to minus 1, 10 to minus 1, 10 to minus 1 mole of HF. And you need exactly the same amount, since 10 to minus 1 is 0.1 molar. They are the same thing, 0.1 mole. Then you have 0.1 mole of sodium hydroxide to neutralize H. Then you may ask, what about the pH value? The pH value is not related for this calculation, baby, because, and you may say that, okay, there is no difference between neutralization of strong acid or weak acid. Okay, there is a significant difference between them. The difference is that the neutralization of weak acid takes place quite slower, baby. But you have to add same amount of base to neutralize them.
Okay.
Because, okay, this is obvious. We have 10 to 1 minus 10 to 1, 10 to minus 1 molar of HF. And we also have 10 to minus 3 molar of hydrogen plus, and this one also. But neutralizing only that much of hydrogen plus is not finished the neutralization job, baby. Because when you decrease the amount of hydrogen plus, reaction will shift to the product side, shift to the forward, and it tries to replace the consumed up hydrogen plus ion by ionization. To complete, to finish neutralization, you have to finish all hydrogens, even not ionized, in HF form. Did you get the idea, baby? Because we may say that the pH for weak acid can be stated as free hydrogen plus concentration, but we have plenty more as not ionized. And neutralization of only free ions is not resulted as full neutralization. The full neutralization is real neutralization. Real neutralization means to reacting whole hydrogens, even not ionized at the beginning of the neutralization reaction, maybe.
Okay.
Because while you are consume hydrogen ion plus concentrations through the neutralization, as you decrease the concentration of hydrogen plus, the reaction will try to replace them by ionizing more. And due to the fact that the original free hydrogen ion concentration means nothing for neutralization issues, baby, okay?
Okay.
But what's the difference? The most significant difference between the strong acid and weak acid neutralization, as I told you before, the neutralization reaction for weak acid will complete it up fastly. For example, it will take, let's say, 10 seconds. But for the upper one, it will, the duration of reaction, couple of minutes, maybe 2 minutes or 5 minutes, something like that. And due to the fact that the temperature difference, delta T, for reactions is quite different. For example, the delta T, we know that the whole acids and base reactions are exothermic, and they should followed by temperature rise, and temperature rise for upper one will be more than that of lower one. Why? Because since we are doing this experiment, let's say in room temperature, and while neutralization, we are mixing up two solutions, and we left them on the bench, and we just want to measure the temperature rise. While doing this one, our system will lose some amount of energy to the surrounding. And since our reaction is something slow, then the heat loss to the surrounding is quite significant. Because of that, okay, they will produce same amount of Q, same amount of energy. But when our reaction takes a slow and more time, then it has more time to lose energy to the surrounding, baby. Due to the fact that the temperature rise for weak acid neutralization is not as much as we expected.
Okay.
Okay, why? Because we have heat loss to the surroundings. Okay, baby, this is the case. Then we may conclude up what? For strong acid, the pH will be what? Will be the same as concentration. Okay? Then neutralization is the same as acid, and also it's fast. Due to the speed of reaction, the delta T will be high. Okay? For the case for the weak acid, the pH will be higher, higher than the original, higher than original acid concentration. Higher means closer to the neutral case. And neutralization reaction is slow, but same mole of base required. Okay, this slowness will observed as the temperature difference is just below than we expected. Okay, this is just the case for weak acid and strong acid case. The same thing can be said for base case, base scenario. They are the same. They are almost the same. But for the calculations of weak bases, we have Kb value, baby. Instead of Ka, we have Kb value. The rest of the quite the same. We have what? We have MOH type of thing. Then we still have an equilibrium. Then we have M plus and OH minus. Then we have 10 to 1 minus 1 molar of original base. And let's say this one is 10 to minus 4. This one also 10 to minus 4. Then this will be the calculation for Kb instead of Ka. Then it will be 10 to minus 4 times 10 to minus 4, blah, blah. The rest of the same, baby. Just the same. But we just find POH as 4 instead of pH. And if we want to change this one to pH, which is simply 10. But normally, what we should observe the POH of 1 while pH is 13. Okay, this is the same thing, just exactly the same thing. And we may say that the ionization ratio for weak base can be calculated. Yes, it can be. We may say that 10 to minus 1 molar of base will produce 10 to minus 4 molar of ion. And 100 will be it will be something 0.1%, something like that. Okay, baby, they are the weak acid and weak base calculations are the same. Just for the weak base, we are dealing with POH instead of pH.
Yes, okay.
Okay, they are the same. And I just want to advise you to watch our video before our next lesson, babe, okay? Because the next one will be really, really challenging.
Okay.
Okay? What was today's lecture, babe? How is it? Is it good or quite challenging?
It wasn't easy, but I think it was understandable.
Then I promise you, the next one really calculated.
Okay.
I know so many chemistry teachers cannot able to understand what's going on while doing buffers and hydrolysis reactions, maybe. Next lecture, we will cover up hydrolysis and buffer reactions. They have one difference. Okay, this difference is understandable, but calculations are not simple, okay? Okay, I advise you. Be really prepared for
Okay.
next day, okay?
Okay.
Okay, baby. See you.
See you. Bye.
Bye-bye.